next data frame. And we have seen that we have two protocols. One is stop and wait protocol, and another is sliding window protocol. And in stop and wait protocol, what we have seen, the only one data frame is being sent one at a time, and after receiving an acknowledgement, the second packet is being sent. And we have also find out the link utilization efficiency in case of stop and wait protocol. And there what we have seen, the link utilization efficiency will be, what is that? U, if we termed it by U will be equals to this 1 by 1 plus twice A, where A is TP is the propagation delay time, R is the data rate, and L will be the length of the or size of the data frame. Now, from here, what we have seen, if A is lower, then the link utilization efficiency will be higher. And when A will be lower, if the size of the data frame or length of the data frame, which is denoted by L, it will be large. But large data frame, sometimes it is prone to error. So, and link utilization efficiency, this efficiency can be increased by sliding window protocol, what we are going to study now. But in GIST, the sliding window protocol means the the sender will send the data frames without waiting for the acknowledgement from the receiving end side. And when it receives an acknowledgement, it will acknowledge all the previous data frames. So now we are going to study sliding window protocol. In sliding window protocol, why we call this to be a sliding window? Because here both the sending end and the receiving end will maintain a window, and this window is characterized by three parameters. One is upper edge window, second one is lower edge window, and the window size. Now here, so the physically the window, that is why three parameters: lower window edge, upper window edge, and window size. Now if we see the diagram is clearly visible. Hello? Hello?
Yes, ma'am.
Yes, ma'am.
So here, what we have seen from the figure, this is the transmit window and this is the receive window. Both the transmit window and receive window are of size 7, because within a window it will contain 7 data frames, which is and each data frame is mentioned by a sequence number. So here, and D0 will be the lower window edge and D6 will be the upper window edge, and the window size, therefore it will be 7. Similarly, the receiver, both the transmit window and the receive window are of same size. Since it is D0 to D6, here also it will be D0 to D6. Now, and here the acknowledgement is given in terms of frame, which name is RR. This is RR. R means receiver ready. And the RRN, if we acknowledge the data frame by RRN, where RRN stands for, RR stands for receiver ready, and N is the sequence number of the data frame the receiver is expected to receive from the sender. That means if the receiver ready 2, that means 2 is the sequence number of the data frame which the receiver will expect to receive from the sender. Now here, why we call it sliding window and how the data can be sent without waiting for an acknowledgement, this has been explained with the help of this figure. Now, since we have taken the window size 7, that means within a window we have 7 data frames, and these data frames have a sequence number D0, D1 up to D6. Now, when the sender will send a data frame, it will send a D0, and D0 is being received by a receiver, and this data frame is copied inside the window. So here this box will be without any dotted line, and the rest of the windows, it is shown as a dotted line because we are not yet received the frames D1 to D6. Now next, without waiting for an acknowledgement, the sender will send a frame D1, and D1 is being copied in the receive window. Now, from the sending end side, what we have seen, D1 is being copied and the receiver send an acknowledgement which is RR2. That means receiver is ready to accept the data frame 2. And it also indicates that when the receiver will send RR2, it means, and when the sender will receive this RR2 frame, it means that both D0 and D1, this frame is being received by the receiver without an error. So this is the form of an acknowledgement in case of a sliding window protocol. Now, without waiting for a receiving of RR2, the sender will send the D2. Now, while it is sending D2, it receives RR2. Then the sender will know that D0 and D1 have been received correctly, so it will slides its window. That means it will remove now D0 and D1 frame from its window, and it will enter D7 and D8 frames which are waiting. So after receiving this acknowledgement, the window slides which was previously from D0 to D6 in the figure, it will now slides to D2 to D8. Now, why D2 to D8? Because we have a window size 7. Now, then at the receiving end side, the receiver receives D2 frame, and D2 is being copied. And when it sends RR2, when the receiver sends RR2 at the receiving end side, that means the D0 and D1 frame will be received correctly. So it will slides its window from D2 to D8. So after the receiving of D1, when the receiver sends RR2, it means that D0 and D1 frame received correctly, and the receiver slides its window from D2 to D8. Now when the receiver receives D2, D2 is being copied here. Similarly, here the sender will send a D3 frame. D3 is copied here, and sender will send a D4 frame. D4 frame is copied here, and RR5 it indicates, and when it receives D4, it is copied, the receiver will copy it here and sends RR5. That means this also acknowledges that the frame D0 to D4 has been received correctly, and the receiver is waiting to receive the data frame D5. Now, even if this RR2 is being lost, if the receiver sender doesn't receive an acknowledgement, which is known as RR2 from the receiver, but the next release of an acknowledgement, which is in the form of RR5, it will acknowledges the receipt of all the previous data frames correctly. So is it clear what we mean by now here? Now, since the window slides as we receive the data frame correctly, so this is known as sliding window protocol. And here is the difference lies from stop and wait protocol, where we are going to send a data frame one at a time, and but here without waiting for an acknowledgement from the receiver, the sender will send a data frame with respect to that of stop and wait protocol. So if the link has been established to carry large number of data, that means data rate will be more, then here that link utilization will be utilized more than that of stop and wait protocol. So is the sliding window protocol is clear to you? And
Yes, ma'am.
okay, and you have understood that how the link utilization efficiency could be increased by sliding window protocol?
Yes, ma'am.
Okay, clear?
Yes,
Okay, then
ma'am.
we move on to next topic. Now, if an error occur in a data frame, then how could the sender will know that the error has been occurred in a data frame? So, and this is known as error control. How the error could be detected and corrected, which means error control in both stop and wait protocol and sliding window protocol. Now, these error control mechanism are is different in stop and wait and in sliding window protocol. Now, first we come to the how we, if the data frame receives with an error, how the receiver will tell that the sender that there is an error in a data frame. So to retransmit the data frame again, this here we are having two mechanisms. One is by adding a timer. First one, now why we are going to add a timer? Now, when the sender will send a data frame in case of a stop and wait protocol, it will start a timer. And first one, when the data packet is lost, and this can be displayed here, say when the sender sends a data packet, it will send the data packet 0, and the receiver will receive the packet 0. And when it will send an acknowledge upon receipt of the packet 0, it will send ACK 0, and the receiver will receive ACK 0, and then it will send a packet 1. Send packet 1, which with a, that means the sequence number of the packet is 1, and this packet is lost in transit, or it may come to the receiver with an error. Now, when the receiver receives the data packet with an error, it couldn't able to send an acknowledgement. So now, since when the sender sends each packet, it will start a timer. So after time out, which is this time out, this time, that means from here to here, this time is known as round trip time. That means from sender to receiver and then back to the sender. So it will wait for this amount of time, and then it will resend the packet one again after time is being out, or when the RTT, round trip time, is being over. So it will receive, it will again send packet one, and it is received correctly now. And then it will send an acknowledgement, and the sender will receive an acknowledgement, and then it will send the next data packet. So in this way, if there is an error in a data packet, or if the data packet is lost in transit, the how the correct data frame is being received by the receiver, this is in the form of adding a timer at the sending end side. Now this is when data frame is lost. Now what happens if an acknowledgement is lost or delayed? And this has been shown here. So here the sender will send the packet 0, and it will receive the packet 0 with correct. There is no error in this packet, and it receives SEK 0. Then it will send the packet 1. It will receive packet 1, and the packet 1 is correct. So it will send an acknowledgement and SEK1 to the sender, but this acknowledgement packet is being lost in transit. That means then what sender will do, it will wait for a round trip time. If within this time it hasn't received the data packet, it will again resend the packet 1. So, and when the receiver receive this packet, it will discard the duplicate packet and send an acknowledgement to the receiver, and then it will send the data packet 2 again. This is if the acknowledgement is lost in transit. Same thing happened when the timeout has been occurred in receiving SEK frame. That means here also sender will send the data packet. When it receives correctly, the receiver will send an acknowledgement. Then the sender will send next data frame. The receiver received it correctly and send an acknowledgement, but it has come to the sender delayed. That means after round trip time has been occurred, or completion of RTT, round trip time. Say sender will know that since it doesn't receive the acknowledgement SEK1, then it will resend the packet, and it is again duplicate packet, and that duplicate packet is being discarded by the receiver. And when it receives SEK, delayed SEK1, it will send the packet 2. So clear how we control error if there is
Yes,
a
ma'am.
error in a data frame, or SEK is being lost or delayed. Now the disadvantage of stop and wait, the efficiency is very less, because with respect to sliding window protocol, link utilization efficiency is less. Only one frame is sent at a time, and timer should be set for each individual frame. Both the sender and receiver window size is 1. this will be the disadvantage with respect to sliding window protocol. And because in that in sliding window protocol, the sending and receiving window size will not be 1. But in case of uh, disadvantage over receiver window, this sender window side is 1 in case of a sliding window protocol. This is disadvantage over go backend. Now when we are going to study how we can control error by go back in protocol in which is under sliding window protocol, so it has been mentioned here that sending window size is 1, so it is disadvantage over go backend, because in go backend protocol, which falls under sliding window protocol, to control the error in the data frame, the sending window size will be more than 1. Here in sliding window stop and wait, the receiver window size is always 1, and disadvantage over selective repeat, because in selective repeat protocol, which is again under sliding window flow control protocol, the receiver window size will be more than 1. So that is why this will be the disadvantages of stop and wait over sliding window protocol. Now we come to the error control in sliding window protocol. Now here, just like we can control the error in the data frame by adding a timer or by when the data frame is lost, what we are going to do, that has been shown. And when the SEK is being lost or lost and received after RTT, how we can take care of that data frame, that we have seen. Now here, to control the error both in the data frame or the acknowledgement frame lost or delayed, the two protocol is being used under sliding window, which is known as go back in, and another is selective retransmission. Now these two protocols are different. Now let us study these two protocols, which is go back in and selective retransmission. Here also we are going to take care of loss of data frame and loss of RR or REJ. Here, besides receiver ready acknowledgement signal, it will also send an REJ signal if the data frame is being lost in transit, or if the data frame is received with an error. This is reject frame. Now when RR N, it stands for, the N is the sequence number of the data frame the receiver is expected to receive from the sender. But when we put REJN, N is the sequence number of the data frame which is lost or which is received with an error. So you clearly understood what we mean by RRN and REJN.
Yeah, ma'am.
Now here, this is the go back in protocol. Now here also, since it is under sliding window protocol, so both the sender and receiver will maintain a window. Here the transmit window and the receiver window are of different size. From the figure we have seen, here the transmit window is of size M, because within the window we have 7 data frames which is being numbered as D0 to D6, and this is the lower edge window, and this is the D6 is the upper edge window, and the window size is 7. This is the sending end window size, but the receiving end side, the window size from here, what we have seen, the window size is 1, which is same as that of receiving window size in stop and wait protocol. Now let us see why we called it to be a go back N. Now here the window size is 7 and we have a data frame D0 to D6 within the window, and the sender is sending a data frame D0, and D0 is copied in the receiver window. Now when the receiver receives D0, it will send an acknowledgement, say RR1. That means the receiver is ready to accept data frame which is D1, because 1 is the sequence number of the data frame the receiver is expected to receive. So it will need certain time. Now at the sending end side, the sender will not yet receive RR1, and it will, without waiting for an acknowledgement, because this is the principle of sliding window protocol, the sender will send a data frame D1. Now from the figure, we have seen the D1 is being lost in transit, or it may be received by the receiver with an error. Now when the at the so it is not being copied here, so this window size, this D1 frame, it is shown as a dotted line. Now at the sending end side, what we have seen, when the receiver when the sender received the frame RR1, it means that D0 and D1 is received by the receiver correctly, but it didn't know where the data frame D1 is lost or data frame D1 is being received by the receiver with an error. So it will shift its window from D0 to D6. Now it will be from D1 to D7. So now the sender will send a D2 frame. Now when the receiver receives the D2 frame, it knows that D1 is being received with an error, and it will send an acknowledgement, this which is in the form of a reject. So reject 1, that means since D1 is being received with an error or it is lost in transit, so this will be the sequence number of the data frame which has been lost or received with an error. Now receiver receives D2, but since D1 is being lost or received with an error, so it will not copied the D2 frame. Still the D1 is shown as dotted line, then and the sender then sends, since it is a without waiting for an acknowledgement, it will send the data frame. So it will send a D3, but still the D3 frame is not being copied by the receive window, though D2 and D3 received by the receiver correctly. Now, when the sender receives an REJ1, then only it knows that there will be an error in the data frame or it has been lost in transit. So it will again send a D1 frame, and when the receiver, now the receiver receives D1 correctly, it will copy that D1 in its window and sends an acknowledgement RR2. That means the frame D0 and D1 receives correctly. What happens to the sender before receiving RR2? Still the window will be maintained within D1 to D7, because here RR1 it stands, that means D0 frame is received correctly, so the window slides to D1 to D7. Now during this time the window size will be from D1 to D7, and when the sender receives RR2, it means that D0 and D1 will receive correctly. So it will slides its window D1 to D7 to D2 to D8, and it sends D2, D3, and so on. So why it is called go back N? So until and unless the frame which has been lost or received with an error, if it is not received correctly by the receiver, there will be, it will not accept the data frames which followed D1 frame, though that means the data frame which is after D1 will be D2, D3, D4, and so on. Though it will be received by the receiver correctly, it is not being copied in its window unless and until it will receive the data frame D1 which has been lost or received with an error correctly by the receiver, and then it will again send D2, D3, and so on. So that is why it is known as go back N. Clear? Hello? Hello?
Yes, ma'am.
Clear to everybody? How many of you are attending? Only 6 or 7, I think. Yeah, now it is 5. See, 14 people, you are 14, your strength is 14, but my class, the out of 14 only 5 is attending my class. Okay, so so is it clear to you why we call it go back N protocol? Now this is for the loss of data frame. Now what happens if acknowledgement frame is being lost? Now I have told you the next acknowledgement receives by the sender, it will acknowledges all the previous data frames. So if RR1 is lost, the next acknowledgement frame, which is RR2, acknowledgement is received when the frame is being RR received without lost and without an error. So RR2, it indicates both D0, D1 is being received correctly, or RR3, it indicates both D0, D1 and D2 received correctly, and so on. So in this way, we can take care of sorry, loss of RR1, or if the delayed receipt of RR1, just like in case of stop and wait. But what happens if REJ is being lost or delayed? Now when here also the receiver will maintain a clock, and when it sends a frame REJ1, say which has been received from the sender with an error or which is being lost in transit, it will start its timer, and after a timeout, if it is being lost or delayed, so after timeout, just like in stop and wait, it will again send a frame REJ1. So this is the way we can take care of if the data frame is received with an error in case of go back in, and if RR or REJ is being delayed or is being lost. Clear? Now we come to the selective retransmission. Now you will see there will be a difference in go back in and selective retransmission, and why we call it selective retransmission. Now here both the transmit window and the receiving window are of same size. Now here the window size in this example, I have again taken the window size of both the transmitter and the receiver, or sender and a receiver are of window size is 7. So it is from within a window we have D0 to D6, and D0 is the lower window edge and D6 will be the upper window edge. Here also same thing, D0 to D6 window size is being 7 because the transmit and receive window are of same size. Now here also when the sender sends a frame D0, first the receiver will receive the frame D0, and D0 is being copied inside the window, and it will send an acknowledgement RR1, and without waiting for a receipt of an acknowledgement, the sender will send the frame D1 and it has been lost, so it is not being copied here. Now here at the sending end side, when the sender will receive RR1, that means that the D0 is being received correctly, so it slides its window from D1 to D7, which is previously from D0 to D6, and it will send a frame D2, and D2 is being copied here. Whereas in case of go back in, what we have seen, if the frame is being the frame which has been lost, the receiver will not accept the other the data frames followed by the frame which is being lost. But here the receiver will accept the data frame followed by the frame which is being lost. So it receives D2 and D2 is being copied here. Now then the receiver will know that the D1 is being lost in transit, or it has been received with an error. So it will send a signal which is selective reject 1. That means data 1 is being lost. Data packet 1 is being lost. So, and when the, and then since here D0 and RR1 is being sent by the receiver, the window again slides from D0 to D6 at the receiving end side. I have forgotten to tell you this. D1, it will slides from D0 to D6 to D1 to D7. And it got copied here D2, then it will send SREJ1, and when the sender receives an SREJ1, it will immediately send a packet D1, and then when the receiver receives the packet D1, it will copy this frame here and it will send RR4. And when the receiver sends an RR4, it means that all the previous data frames, that means D0, D1, D2 and D3 has been received correctly. So it will, the receiver window will slide from D1 to D7 to D4 to D10. And then when the RR4 is being received by the sender, since it means that D0 to D3 frame receives correctly, so it will slides its window from D4 to D10 and it will send the frames. So here, without discarding the frames, the following frames which has been received with an error frame, here the all the frames is being received by the receiver and copied in the window, and when the lost frame is being received, then the receiver will copy that within its window and sends an acknowledgement to the sender so that it will slides its window from previous size to from size remains same, but the so that next data frames will be within the window size. Clear? That is why we call it a selective repeat. That means the frame which is being received with an error and which is being lost in transit, that frame will be sent by the sender only, not the other frames which has been received correctly. Whereas in go back end, what we have seen, the sender will send the lost frame as well as though the other frames followed by the lost frames which has been received correctly, it will send those frames again. That is why previous protocol is known as go back end and this is known as selective repeat. Clear? And again also the same thing happens in case of when acknowledgement frame or which is receiver ready frame is being lost. If it is lost, then the next the RR frame will acknowledges all the previous data frames, and if SREJ is being lost, then the when the receiver will send SREJ frame, then it will start the timer, and after timeout it will again send the acknowledgement SREJ frame again. So this is all about the flow control mechanism or flow control technique. Now we move on to the next topic. So which is digital encoding. Now digital encoding means how the digital data and analog data is converted into a digital signal. Now we have here a table. If the data is digital and the signal is digital, it is encoding. analog data, and digital signal. It is also an encoding technique, but analog it is modulation. Digital analog, it is also a modulation. This is the approaches for conversion of data into a signal. Now, how we convert analog data into a digital form, this technique is known as pulse code modulation. Now, how we are going to convert analog data into digital form? There are 3 steps. First step is sampling, then second step is known as quantization, and the third step is known as encoding. Now, while we are going to sampling the data, what will be the sampling rate? Hello? What will be the sampling rate? Because the first step in converting analog data into a digital form is sampling, then quantization, then encoding. What will be the sampling rate?
At least twice the frequency of the data.
Twice?
Twice the frequency of the data.
Yes, twice the highest frequency component in the original data. That means in the information signal. Now, after sampling, here now we can convert analog signal into a sampled form, or we will get the sample version of the analog signal, which is continuous in nature, by using a sampler. And in a sampler, we have 2 inputs. One is the original signal or a baseband signal or information signal, and another is a pulse train of constant amplitude pulses of very short duration. And then when we fed this to a sampler, which is nothing but a multiplier, then we will get a sampled version of the analog signal, which is being shown here. Say this is the analog signal and this is the sampled signal. That means when we fed this analog signal and a sample of pulse train of having constant amplitude of very short duration, then we will get an output from the sampler. Now, when we will get the output from the sampler, which is nothing but or we take this to be we fed this to an analog multiplier, then what will happen? What will be the output? Say we are feeding baseband signal or information signal plus the train of pulses having constant amplitude and of short duration. Train of pulses. What will be the output from the multiplier? Hello? হ্যালো, আরে বলো কি হবে আমরা যদি একটা অ্যানালগ মাল্টিপ্লায়ারে we are feeding one input of the multiplier, we are giving this type of signal, and another input which have a train of pulses having constant amplitude. Then what will, and this will be the output. See here, the pulses having short duration. And why the previously when we are going to fed a train of pulses having constant amplitude, but the output when we receive, we will get this. Why? High or low? high or low? Why we didn't get the values here? Why we get only? It is quantized. Is it quantized? Is the value is quantized? These values, or these are the continuous values of the pulses? Now, why the output is like this? I am asking. Why we didn't get any values? Because the analog signal is continuous. And why we get, why the time is discrete? Yes, tell me that when there is a pulse, we will get an output. When there is no pulse, there will be no output. And what will be the sampling frequency? It will be greater than or equal to twice the highest frequency component of the baseband signal or an information signal. In order to, why the sampling frequency, or sorry, why the sampling frequency or sampling rate should be so high? Because then we can able to recover or we will get the actual version of the analog signal which has been sampled, isn't it? Hello? So, and this will be the sampling interval, which is shown as TS. So, the output from the analog multiplier, we will get an output when there is a pulse, and when there is no pulse, we won't get any output from the multiplier. So, the output, what we get, and this is known as pulse amplitude modulation. That means amplitude of the pulses previously which is fed into the multiplier having constant amplitude. Now here the amplitude of the pulses is being varied with the amplitude of the analog signal. And the envelope of this pulse amplitude wave resembles the analog signal. Clear? Because here we have a pulse, so we will get output from analog multiplier. We will get an output, and let this output amplitude of the pulses is value is 3.0. And here again the pulses is present, and during this time there will be no pulse. So the since it is a multiplier, so if we have no pulse, and here we have an analog value, but since it is a multiplier, it is the output is 0. And this is known as pulse amplitude modulation. You have now by this time you have already covered modulation technique. You have understood na in your part 1 course. It has been finished or not yet? Not finished yet. It hasn't started yet.
Yes, it has started, but it's going on right now.
Then what we mean by modulation? Tell me. That is modulation. What is the basic idea behind modulation? Yes, to shift the frequency spectrum of the signal. Of which signal? Okay. So here, and this is known as in amplitude modulation, the amplitude, carry modulating signal is the information signal, and the information, we have a modulation signal, which is information signal or message signal, and we have a carrier signal. And in amplitude modulation, carrier amplitude of the carrier is being modulated with the information signal, message signal, or we call it to be a baseband signal, and so on. And the output, what we get after modulation, is known as a modulated wave. If it is done with, by modulating the amplitude of the carrier, then we call it to be amplitude modulated signal. If the frequency of the carrier is being changed, we call it to be a frequency modulated signal. If the phase of the carrier is being changed, we call it a phase modulated signal, because any sinusoid can be expressed by its amplitude, phase, and frequency. So here, since this we have a pulse trend, in case of an analog modulation, we are using carrier signal, which has a high frequency than that of information signal, and we do modulation to shift the frequency spectrum of the message signal. Now here also the amplitude of the pulse trends, so in and which is equivalent to carrier signal in case of an analog modulation, and this technique is known as pulse modulation technique. And we have a pulse amplitude and any pulse can be characterized by its amplitude, duration, width, and so on. If we change the amplitude of the pulse, it is known as pulse amplitude modulation. If we change the width of the pulse, then it is known as PWM, uh, pulse width modulation. If we change the position of the pulse, then it is known as pulse position modulation, or PPM, PWM. And this is since the amplitude of the pulses is being changed with the analog signal, we call it to be a pulse amplitude modulated signal, or we call it to be a PAM signal, pulse amplitude modulated signal. Now after this, the time is being converted into a discrete form, which is being continuous here, but still the amplitude is being amplitude of the pulses is continuous in nature. So after quantization, we will convert this continuous value into a discrete form. And if we using 3-bit, we can use 3-bit quantizer, 8-bit quantizer, 16-bit quantizer, 32-bit quantizer. That means if 3-bit quantizer, if we have a 3-bit quantizer, then how many levels the signal has? Hello? Yes, that's right. Now here we are using 3-bit quantizer. So and we are using rounding off type quantizer. So this is here at this instant of time, the PAM value has 3.0. So we have quantized value equals to 3. Now, since it is 1.4, so it is equivalent to 1. Since it is 6.22, so since we are using rounding of type quantizer, so the value will be 6. Here it will be 1. Here it will be 3. Here it will be 6. And here it will be 4. So now after quantization, we have, and since we are using 3-bit quantizer, because each value is expressed as in the form of 3 bits, so here the 3 is represented by 0, 1, 1, and 1 is represented by 0, 0, 1, and 6 is being represented as 1, 1, 0, and so on. So this is the PCM, pulse code modulation waveform, which is the conversion of baseband signal into a digital form. So we have this digital data. Now, since this digital data we cannot able to send, but we have to convert this digital data into a digital signal. So, and this technique is known as encoding technique. And there are three types of, and this data is known as PCM data or output, PCM output. So this is the function of a PCM transmitter. Now we have three encoding schemes. That means how we will convert digital data, this digital data into a digital signal, that is known as encoding. And we have three types of encoding scheme. One is unipolar encoding, second is polar encoding, and the third one is bipolar encoding. Unipolar means it has only one signal level. That means here or one voltage level is used because it is unipolar. So here digital 1 is being represented by a voltage and digital 0 is represented by no voltage, or binary 1 is represented by positive voltage and binary 0 is no voltage or idle line. And in this encoding scheme, unipolar, we have RZ, unipolar RZ and unipolar NRZ, which means RZ stands for return to zero and NRZ stands for non-return to zero. And in polar encoding, we have two voltage levels. Binary 1 is represented by one voltage level and binary 0 is represented by another voltage level. A positive voltage level and a negative voltage level is being used. And NRZ, non-return to zero inverted, non-return to zero level Manchester, differential Manchester are examples of these encoding schemes. And next we have a bipolar encoding. It has three voltage levels, plus positive voltage, negative voltage and zero voltage. And bipolar RZ, AMI, HDB3 encoding schemes are example of this bipolar encoding. So let me finish here. We will again complete it coming Thursday. Okay, I
Yes.
am leaving here. Thank you very much, those who have attended my class.
Thank you.
Thank you, ma'am.
Okay, thank you.